This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello and welcome to Software Engineering Radio. This is your host, Sriram Panyam. Today I'm joined by Will Wilson, CEO and co-founder of Antithesis. Will started off in biotech and went on to work on distributed systems at FoundationDB, Apple, and Google. And then he eventually went on to found Antithesis, an autonomous testing platform based on deterministic simulation testing. Will, welcome to the show.
Thank you so much for having me.
For our listeners who may not be familiar with the concept, could you share what is DST or deterministic simulation testing?
Yeah, sure. So let's start with the way that people normally test software, right? So the way you normally test software is first you write some code, and then you try and think about what situations you want to cover with a test, what situations you want to make sure are going to work in real life, and then you write some tests to cover those situations, right? And then you occasionally run those tests. Maybe you do them on every CI build, or maybe you do them on every PR, maybe you do them only when you're about to release your software. But they cover those cases, and you hope that when you deploy to production, everything is going to go okay. Now, let me ask you a question. Do you believe, if all your tests pass, that everything is going to be okay?
I would like to think so.
But do you actually?
Well, if anything, last 20 years have shown me no.
Right. Exactly. So why is that? Well, it's because I just said, you're writing the tests that cover the cases that you thought were important to cover. But the things that are actually going to screw you in production are the situations that you did not think of ahead of time. They're the things you did not think to cover, right? And so what that means is this conventional strategy to writing tests is very, very good for catching regressions, right? If there's something that I know my software does correctly and I accidentally break it in a new version, if I have a test for it, that's pretty good at catching that. But a test is very bad at finding out if my software actually works in the real world in all the unanticipated or unexpected situations that the real world will throw at me. So deterministic simulation testing is a very different strategy, which tries to actually give us the confidence that if our tests pass, things will go well in the real world. And the way it does that is basically by constructing a model of the real world, a whole system simulation where random requests come in and ask your software to do things, and tasks are going to run in random orders, and these requests are going to have slightly randomized parameters. And also the things that happen in the real world that can go wrong are also going to happen, right? So occasionally requests will fail. Requests to downstream dependent systems will fail. Network requests may get delayed or reordered. Threads may randomly pause and run later. The garbage collector may just turn on and that whole node may slow down, right? All the stuff that causes people to get paged in the middle of the night and causes weird production behaviors that nobody can understand, we're going to do all that too. And we're going to do it at a vastly accelerated rate so that we cover many, many years or centuries worth of real world badness in just a few seconds or minutes in our tests. And if our software survives all that and things actually go okay, we're now going to have the confidence to actually deploy and to actually feel like things will be all right when we have it in the real world. The final ingredient to this, the part that makes it deterministic, is our model of the real world, unlike the real world, is perfectly deterministic, meaning it's all driven from a random number generator that's under our control, right? So this is very important because sometimes what happens is there's a particular, let's say that a packet takes 21 milliseconds to get from service A to service B. And if it takes 19 milliseconds instead, something goes wrong, right? There's some distributed race condition, something loses, and as a result, there's some bug that a user can see. You may have great difficulty replicating that situation again, right? Maybe it only took that long because of some very rare set of circumstances. But the determinism of DST means that any set of circumstances, no matter how rare, no matter how unusual, we can perfectly replicate. And so if we see a bug once, we can see it as many times as we want, and we can debug it with very, very high efficiency. How you actually achieve that is sort of the hard part. But once you have it, it's an incredible asset.
Awesome. Thank you. Before I dive in, I would like to get some of the origin stories here. Here it started off in FoundationDB. Could you share some of that background there?
Sure, yeah. So this is sort of a fun story. Basically, actually, even before FoundationDB, my co-founder, Dave Scherer, before FoundationDB had another company called Visual Sciences, which you can think of as having made a very, very early web analytics product that was backed by a very powerful analytic database that's sort of a very early version of Google BigQuery, right? And this would have been in the early 2000s. So it was really very, very ahead of its time. So when Dave was building that big analytic data store, he was really interested in using model-based techniques to look for sort of long tail performance pathologies and like strange sort of high latency corner cases. And so he built this little like model-based simulation of the database to see if he could find these issues. It's sort of like in some ways similar to formal methods, if you're familiar with that, but he was using it to analyze performance rather than correctness. The problem that Dave ran into was, of course, once he had this all working in the model, how do you know that your real code is behaving anything like the model, right? And so that company got sold and that never went anywhere. But it stuck around in the back of his mind. And so then when we were doing FoundationDB, he had the same idea again, this time to use it to study correctness rather than performance. But then he had the further idea, what if we just made the actual program into the model, right? Then you would never have to worry that, oh, I did some analysis on this model and it gave me this result, but actually my real world code has a bug in it, so it doesn't perfectly match that specification. So the trouble is, real world code has things like concurrency, and it has things like it reads the clock and it gets random numbers from the operating system, and it does all kinds of things that make it fundamentally non-deterministic and make it so that if you run some battery of tests or conduct some simulation, the result might vary from time to time. And so we set about writing FoundationDB in a very special way so that it could be perfectly simulated. We did things like we used our own user space concurrency primitives and scheduling so that the kernel was never deciding which task to run. It's like sort of similar to the Node.js concurrency model, but we were doing that in C++ long beforehand. We obviously had to mock out or stub out any form of network communication between nodes and handle that in process. We had a fake clock and a fake random number generator that got accessed instead of the ones provided by the OS. And as we sort of knocked away each of these forms of randomness and each of these forms of non-determinism, the simulation became more controllable until we eventually got to a point where it really was like you could really just run a program and it would simulate an entire interacting FoundationDB cluster with possibly dozens or hundreds of simulated nodes speaking over simulated networks with, randomly introduced networking delays and congestion behavior and whatever else you want. And this was just such an insanely productive mode in which to work. Like, people who are familiar with FoundationDB these days mostly know it for its reputation, which is being one of the highest quality databases ever made, never losing your data, never doing anything wrong. And it's true, we got that. And we got that because of this technique. But the thing that made almost an even bigger difference was that we were able to get that with a very, very small team. Because what this technique enables is like this incredible form of pair programming with the computer, where you write some code and then you run some simulations and you say, did I introduce any bugs? And, if the answer is yes, then like you just try again. It's like having an oracle or a genie that can tell you if your code is correct, right? It's like this incredible, incredible accelerator for an entire team. And that was what made us really excited about this technique. And I think this is why so many others have started adopting it and picking it up as well.
Interesting. That reminds me, as we go deeper, right? I mean, to build a simulation, you need a model. So how do you avoid the paradox of, hey, look, I don't know what I don't know, and I built this model?
Yeah, that is a really, really good question. And basically, the answer is you have to err a little bit on the side of your model being worse than reality rather than better than reality, right?
Could you give an example of that? What worse looks like?
Yeah, sure. So your network in your data center is occasionally going to have periods of being down, and it's going to occasionally have periods where it's a little bit slow. And it's occasionally going to have periods where it's like working great. And these periods in your network are probably totally uncorrelated with what your program is doing, right? And so suppose that there's some bug, and the bug only happens if your program is in the middle of some particular operation, right? Like you're doing some, I don't know, you're doing some transaction on your database, and at exactly that moment, the network does something a little bit wrong, right? Or it's a little bit slower than you expect or whatever. And only if these two things happen at the same time, this bug happens. And let's say the bug is really, really bad. In order to make that bug happen very reliably and very reproducibly in our tests, we don't want to make the network completely uncorrelated from what your program is doing. We want to make it basically as malicious as it can be, right? We want to try making the network bad at each different sort of moment that your program could be doing something. And we want to like artificially increase the probability that this network badness happens at exactly the right spot to trigger that bug. Because that way you see it in your test, like in a few seconds or a few minutes, rather than having to wait for days or weeks, which you would have to do if it were happening in production. And so that's kind of an example of where if you make the simulation more hostile than reality, it can catch stuff quicker than it would happen in the real world, and also ensures that you don't miss things that can happen in the real world.
So what would be a good, I suppose, evaluation or identification function to know when or what a bad network is? For example, a network loss of 10% may be really good in some applications, but really bad in some. So how do you decide?
That's totally true. And furthermore, there can be a very dangerous pattern where if you basically make these parameters like a little bit wrong, right? You could accidentally get yourself in a situation where the simulation isn't really testing anything, right? Consider the corner case where we just make it so the network never transports anything at all. Now your program never does anything. And then all your tests are green because we didn't find any bugs because your program didn't do anything. That would be a bad outcome, right? And so there's a few techniques that we can use to avoid this and to make the simulation really good and really well-tuned instead. One is just let's look at things like code coverage, or the more sophisticated version of this is like behavioral coverage, right? If you have certain corner cases in your code that you know are interesting and are important to cover, you should just log a little message when that situation happens. And then at the end of a test run, we should make an assertion that we're able to see all those messages, right? That we basically got at some point to every one of those situations. And the generalization of that is something that we call sometimes assertions. They're like the dual or the opposite of normal assertions, right? Rather than asserting that something is always or never happening, we're asserting that it sometimes happens, because that's an important indication about whether our test is working effectively.
Is that in a probabilistic model, or is it truly sometimes?
Right. So it's like at least one, right? We're saying that if I run my program 1,000 times, I want to guarantee that I see this behavior at least once. That is a property of my testing system, right? Is like, I should be able to make this situation occur. Like the ultimate guarantor though, is just like, are you still seeing bugs in production? Basically, I think people, regardless of whether they're doing DST or not, if you ever see a bug in production, that is actually two bugs. It's a bug in your program, and it's also a bug in your tests. And you should maybe not solve them in that order. Maybe you should solve the bug in your tests first. Who knows what else it will turn up? And this is like a practice that requires a little bit of discipline to get into. But once you do, it's so incredibly powerful. Just like understand why it is that you didn't see that bug the minute it was introduced. And often it will point to an entire area of your software or of your organization or whatever that is not working correctly.
Mm-hmm. So it sounded like there was a bootstrap phase here for a team to kind of onboard. Let's say I'm running a game, right? A multiplayer game running on the internet. This is probably as low as it gets, right? What would the bootstrap phase for me be to adopt this?
Right. So this gets a little bit into like sort of what our company does. Basically, up until we came around, this technique was very, very powerful, but it was a giant pain to adopt because it required you to do things like mock out your dependencies and somehow take control of like concurrency and scheduling within your program, simulate all of your network connections, right? There's sort of a lot that had to be done. And there were applications and use cases where reliability and correctness was so important that people would do all these things. Like I know of actually quite a large number of people now, because they come talk to me, right? Who actually started doing this in the years after FoundationDB got acquired by Apple. The team at Dropbox that worked on their synchronization technology built their own DST. Tiger Beetle is a very well-known financial transactions database. They built their own DST. It's quite good. A number of people actually in the finance or fintech or crypto space built their own DST and did very good job at it because they really wanted to catch any kind of problem before it hit prod because it could result in losing tons of money. And obviously other database vendors were also doing this, as were a number of teams that got influenced by what we had done at FoundationDB. And by the way, after I went to work at Google, I learned that there were teams inside Google that had done this and just never told anybody about it. So I think this is a technique that's been independently reinvented a few times. But it remained a thing that only very, very committed people who really felt like their program had to be perfectly reliable would do because the adoption costs were high. So our new company, Antithesis, tries to drastically reduce the adoption cost for this style of testing by basically solving two of the problems that you and I have already discussed. One is, how do you take an arbitrary collection of software and make it deterministic, right? And prior to us being around, that took a lot of work. And what we've done is write a hypervisor, which is deterministic. And you can take an arbitrary collection of software and just put it in the hypervisor, and now it's deterministic too. And so that already on its own makes this much easier. The second problem is the one you touched on, which is, what's the right network drop rate, right? What is the right way of tuning all these parameters of the simulation to find all the bugs and to find them as quickly as possible? This is like a very hard optimization, machine learning, science problem. And it's sort of unreasonable, in my opinion, for every team on Earth to try and solve this independently. And so we have also just done a huge amount of research and a huge amount of development to make this simulation like self-tuning and to make it very intelligent and very good at finding the correct parameters and the correct settings. So you just don't even have to think about that. And so the goal here is to make it much, much, much easier for people to adopt this stuff, which hopefully just makes them a lot faster at writing software and also produce much higher quality software.
I want to quickly touch back on a point you mentioned about the costs, right? What were the both costs for these organizations to adopt DST in their own setting, engineering-wise, financially?
Yeah, I think if you don't have a solution like Antithesis, then the question is really dominated by your dependencies, right? Because the hard thing about DST is that unless you have a hypervisor, you need to somehow make it so all your dependencies are deterministic too. And that really does just hugely limit what you can do. Most software in the world is not deterministic, right? It's got concurrency, it's got threads, it checks timers, it does all kinds of stuff. When we were developing FoundationDB, we were so influenced by this DST style of development that we actually started removing our dependencies to make it easier to test in this way. So very early versions of our database were using Apache Zookeeper for coordination, for instance. And that just became a thing that we could no longer accept because it made it harder to simulate. And so we deleted Zookeeper and wrote our own Paxos implementation that could be simulated. And that made sense for us. But that's a very, very hard thing to ask somebody to do if they're just starting to adopt this technology, which is one reason that I think that thus far it's only happened in relatively specialized places.
It's almost like asking them to reinvent or re-implement what you guys are doing.
Yeah, that's right. It's just a very high barrier to entry, and that's what we're trying to fix.
Fair enough. That brings me back to the hypervisor that you had mentioned. I mean, can you tell me more about that?
Sure. So we started from the question of how could we make DST easy to adopt? And it's like, well, we need to make it so that everybody can make their program deterministic super easily. And then it's like, well, if your program's written in Java, you could try and make a deterministic JVM. And if your program's written in C, I guess you could try and make a deterministic Linux user space, right? Actually, Facebook did that. That project's called Hermit. But we're going to have customers who use every language. So we can't just play whack-a-mole here doing all these things. And then it's well, so much of the value is being able to test microservices, where service A is talking to service B over a network. But now we need to make that networking deterministic. How are we going to do that? Oh, wow, we need some crazy networking library that we can drop in, but everybody does networking differently. How do we, right? So very, very quickly, you get to well, I guess we should try and get under all of these things and make a deterministic operating system. But then you hit another problem. Well, first of all, not everybody in the world uses Linux, and we would love to be able to have customers on Windows someday and so on. But also the interface between the Linux kernel and everything running on top of it is really complicated. And it's always changing, right? And so maintaining a perfect deterministic Linux as a small company just seemed like a very tall order. And then we were like, you know what? You know what is a very simple interface that has not changed in 40, 50 years? The x86 CPU instructions. So let's just get under the operating system and let's emulate a deterministic computer where no matter what the operating system does, no matter what interrupts it sets, no matter how it, is managing memory or doing anything from the outside, or rather from the inside, it's like living in a perfect, isolated, hermetic, deterministic universe, and it can't actually cause any non-determinism. And then once you build that, it's so easy to adopt. Now people don't have to change their software at all. They just give it to us, we run it inside the magic box, and it's perfectly deterministic. So it's really very, very powerful.
How does this overcome this box is still in isolation or is external to your TCP stack itself or the network layer itself. So how do you reconcile that?
Right. So basically what we do is we take our customers' multiple microservices, right, representing a bunch of different physical nodes in their compute backend, plus whatever their dependencies are. Maybe they have a database, or maybe they've got some API server or whatever. And we take them all and we put them inside the same guest in operating system environment, which is Linux. And then we connect them over TCP locally inside the VM, right? So they can speak over network connections between different Docker containers running all in the same version of Linux. And then we can actually reach in and interfere with those network connections, right? We can slow the packets, we can drop packets, we can do whatever. We can create simulated partitions, we can correlate all this with the code that's running, right? The thing I told you before. Because we see what code is running because we control the operating system. And so it's actually a very complete solution. It works very well. The one thing that's a little bit of friction is if you are highly dependent on some third-party web service that you cannot put in a container and have a hard time mocking. That is going to cause a problem. So we try and reduce that friction for our customers also by writing very good, very high-quality mocks for a lot of common web services. So for example, we have a whole fake AWS that we can run inside the simulation with you. And if your program uses AWS, it just runs in there and uses the fake one and can't even tell the difference. We actually test our own stuff that way because we're very heavy AWS users. We can do the same for Snowflake and GCP and Stripe and whatever. We can write a good mock for it. And that's nice because basically just a few of those covers the vast majority of APIs that people use. And if there's a long tail, I think we'll get to it someday. The other thing that the hypervisor gives us, which is very, very powerful, is extremely efficient and rapid snapshotting and restore of the whole state of the guest operating system, right? So if you use a VMware hypervisor, for instance, you can snapshot that VM and then you can reload it, right? And that takes a little bit of time, but you can do it. Our hypervisor is optimized to perform that operation incredibly quickly and efficiently. More than that, even, when it's running multiple VMs simultaneously on the same computer, those VMs can actually address the same physical memory if their local version of that memory hasn't changed, right? So we're basically doing copy on write on all of the memory of the guest operating system. So now if we run 100 VMs in parallel on the same machine, they're not using 100 times the memory. We're basically like deduplicating all of the memory between all the different VMs, which is a thing that I don't know anybody else whose hypervisor can do that. I'm sure there is one somewhere. But what it means is that we can now test your stuff really efficiently, right? Because we can use huge amounts of parallelism without drastically increasing the memory requirements, which just at the end of the day means that we can find bugs faster and we can find rare bugs faster.
It's interesting because the implication of this means that, hey, you're kind of running the entire customer world in a single sandbox. And you can also do things like simulate connection between A and B if it was in the same zone or same region or even across regions. Because you might know that, hey, look, this is for DR and for various kinds of fault tolerance, right?
That's exactly right. All that we have to do is really change the latency, right, on the virtual connection. Or
and error rates.
And error rates, that's right. And also, correlated failures, right? We'll make things in the same DR region fail together more often, but not across regions. And people use us to test DR all the time. People also love using us to test live upgrades, because that's a very scary situation for many teams. You have some big service deployed and you have customers who are using it, right? And you want to incrementally upgrade your cluster. And while the upgrade is rolling out, you're going to have servers with both the old version and the new version serving requests simultaneously. Does that all work? It can be very hard to test that, but it's quite easy to test it with our environment.
Interesting. So 2 things here from a quote unquote cost perspective. What is the biggest installation that you've run so far on this? Like, how many services, how many instances, RAM, cores?
Yeah. So the biggest one that I know of, so we have a customer, WarpStream, which was recently acquired by Confluent. Yeah. So I think they may be our largest one. So they developed like a Kafka replacement with blob storage on S3, right? And so we started out just testing their Kafka replacement and making sure that that was good and the things that were really durable and so on. And then what happened was they added all the rest of their SaaS architecture into the simulation as well. So the same simulation is not just testing their Kafka and their operations with S3 and so on. It's also testing like user signups and like, people using their admin APIs to like create clusters. And it's like totally crazy. It is actually far beyond what I've ever done with DST, but it works.
How big was it?
I would have to go look it up. I do not know the answer off the top of my head. But I think there were like many different services involved.
Okay, fair enough. In terms of their own testing phase, typically how long do customers run this for? Is it a parallel thing? Is it an ongoing thing? What is the workflow for them?
Yeah, that's a great question. So I think there's 2 main ways that people do this. And one of our long-term product goals, actually not even long-term, one of our relatively short-term now product goals is to bridge these 2 ways of using it. So the first way people use this is sort of offline as a very intensive check phase, maybe overnight, right? Or maybe like they do tons and tons of testing right before release, before rolling out a release, right? So the idea here is like you spend all day writing code, and then whatever the last version of your code is, the default branch, you send that to us when people leave work, and then we test it all night, and then in the morning you come in and you see what your results are. And that can be cool. It does mean that we can find pretty rare, pretty hard to find bugs because we're testing for 12 hours or whatever. But they're still fresh in your head, and it's probably code that you changed yesterday, so it's still high productivity to work on those problems. The other way of using it, which is much more similar to the way that we used it at FoundationDB, well, I guess we actually did both there, but the other way of using it is in the loop, right? Like while you're coding. So you write some code, you make some change, you kick off a test. And hopefully, if you want to do it this way, you need to make it so that your tests can run very fast or can give you good information very quickly. So that hopefully, like within 15 minutes or maybe an hour at most, you get some answer that's like, was there anything obviously broken with this, right? And that can be a very, very powerful iteration loop. I think the ideal is to have both. And moreover, to have them be working together. It would be cool if, like, for example, you are submitting builds throughout the day and you're running tests on them. And anything which at the end of the day, you're still iterating on, but which was green, which we didn't find a bug yet. Overnight, we do like hundreds more hours of simulation, CPU hours, and look much more deeply for bugs in any of those versions, then give you a report when you get in the morning, and then you can sort of pick up where you left off. I think that would be really cool, and that's sort of what we're aiming to get towards.
Interesting.
Can your software engineering team plan, track, and ship faster? Monday Dev says yes. With Monday Dev, you get fully customizable workflows, AI-powered context, and integrations that work within your IDE. No more admin bottlenecks, no add-ons, no BS. Just a frictionless platform built for developers. Try for free at monday.com/dev. You'll love it.
You brought up correlation with the code base earlier. Tell me more. At what level is the correlation? Is it at the compiled binary level? Is it at the actual source code level based on coverage? How does that work?
Right. So basically, we have very good integration with a large number of different language tool chains. So it works a little differently depending on the language. Some of the languages, we actually just come in and like transform your binary afterwards, and you don't have to do anything at all. Like we do that for Java. Other languages, like we give you some flags that you pass to your compiler. Like for instance, we do this for C++ and Rust. And the result in either case is the same binary that you would run in production, except it tells us when each line of code gets reached, right? So far, this is very similar with instrumenting for code coverage or something like that. But the key is we're not just going to use this for reporting coverage to you. We're also going to use this for this kind of correlation stuff for saying, oh, we're in like code block A. We've never tried pausing a thread while we're in code block A before. Let's do that now. Or like, oh, this microservice is running function X, and simultaneously this other one over here is also running function X. Let's interrupt the network connection between them right now and see what happens, right? And we're going to do that very much in parallel. And then the fact that the hypervisor lets us cheaply snapshot and restore stuff means that we can go back to situations that we found interesting and try exploring more from that point. And that basically lets us amplify the probability of very, very rare events to find really, really hard to discover bugs. I'll give you a concrete example because that was a little bit vague. Suppose you have a bug, and in order for this bug to happen, you need to be in the middle of a transaction rollback, and there needs to be some network problem, and right at that moment, something has to trigger a leader election in your cluster or something. If each of those events has a 1 in 1,000 chance of happening at any given moment, that's like a 1 in a billion bug, right? That's like very, very hard for a test to find normally. But if you're running it in production and you're running on thousands of nodes and whatever, like your customers will totally hit that bug. So this is like a classic example of a bug that normal testing would never, ever find and that would cause you to get a page. And so, but what we can do, because we can see what code is running, is when we hit that 1 in 1,000 transaction rollback, we're going to say, aha, we made a transaction rollback. We've never seen that before. Let's do more testing from this point onwards. And each of the tries we do from that point, if it doesn't hit the next event of interest, we can just reset to the transaction rollback and try more stuff from there, right? It's like if you're playing a computer game and you can save your game anytime you want, it's easier to make progress because you can always just reload your game and go to the point where things were going well. And so basically what this means is that for these bugs that require multiple different rare things to happen in sequence, we can find them at a vastly accelerated rate compared to traditional techniques.
You know, I love the example of the saving the game and going back in. I spent my 90s doing that in all those old games.
Yeah, well, so we actually use computer games a lot for testing our DST. So we believe that a good testing system should be able to beat a computer game in the interest of testing it. And indeed, if you go to our website, we have many videos of Antithesis playing classic computer games and beating them.
I saw the Mario example at SRCon last year. So back to the example, right? So what he said was, when you hit that 1 in 1,000 transaction rollback scenario, you still need that scenario to be hit. Is there a way you can kind of say, look, this block of code actually through some sequence of code paths could get hit, and can you force that to happen proactively instead of waiting for it?
So that's a great question. We try very hard to make it so that everything gets hit. And there's a number of techniques that we use to do that, right? One is a very underused technique called swarm testing, which is applicable to people who are not even doing DST. Just everybody needs to know about this technique. Okay. And so the basic idea of swarm testing is you sometimes should run all of your tests with certain features of your program turned off. That sounds counterintuitive, right? Why would you want to do that? Well, imagine a situation where, let's say you have some data structure and you have two randomized operations that you can do on the data structure. One of them adds an element to it and one takes an element out, right? If both of these things happen with 50% probability, the contents of the data structure will never get very large. You would require, like, let's say you want to get 100 things in the data structure and then like some garbage collection routine or some compaction happens. That would require a 1 in 2 to the 100 chance to happen if you're randomly adding and removing things. But if we just temporarily disable the remove function, then you're guaranteed to get a whole bunch of adds in a row, and then you're going to trigger that compaction routine, right? And so this is like a very motivating example, and it's like you want to do this with everything, including with your fault injection, right? One of the most common mistakes that in the early days, before we did this automatically, that customers would make is they would say, I want my code to be maximum powerful, so I want to turn on every single fault. And the problem is there are some faults that will hide bugs, right? Like imagine there's a bug where your program gets into some really bad state, but if you restart the program, the bug goes away. Well, now if we are doing a fault that occasionally kills nodes, that can hide that bug, right? And so what you actually want to do is sometimes run with killing nodes completely turned off, because that might save you from some bug. And so it's exactly the same with everything else, and with what kinds of requests you generate and every other kind of behavior that you want to provoke in the system. Now, it's still possible to get this wrong. It's still possible to overlook things. And so that's why we come back to like the sometimes assertions, the logging, that kind of stuff. If you know that transaction rollbacks are an important situation, you should be adding, a sometimes assertion or a log to your rollback function. And then we should be looking at every test run and saying, did we make rollbacks happen? And if not, that should be a red test failure, right? It could mean that your program has changed. Maybe you accidentally disabled the rollback function. And that's, now we found a real bug. But it could also mean that the tests are weak, right? It could mean that for whatever reason, we're not making transactions roll back enough. And that could be very, very important information.
So in that example of the transaction rollback, the other triggering event was a leader election, right? So again, how do you draw the correlation of what's happening at the lowest bits and bytes level to at the more application level? How do you say that, hey, that actually is a leader election?
Yeah. So the easiest way to do this actually, so the way that requires the least investment from a user is you just look at lines of code. Every line of code in your program has a purpose. Some of the lines of code are very boring. They run all the time, right? The code that like logs a string, that probably is running all the time in your program. And so we're going to see it running all the time, and we are quickly going to get bored of it.
Across all the programs.
That's
because
right.
Leader election would be an external event or external service.
Totally true. But anything that runs rarely, that runs only sometimes, or that runs in very specific conditions, or that runs, you could also have, for example, a line of code that very commonly runs together with some other line of code, but very, very rarely runs by itself. That could be something very interesting. So you're not just looking at which lines of code run or don't run at all, but you're actually also looking at the correlations between them and when they run together with each other or not, and what orders they run and so on. And this is a kind of analysis that human beings are very bad at doing, but it's a kind of analysis that AI is actually very good at doing, machine learning and so on. And so you can sort of look at the history of what the software has done and then ask, is this novel? Like, is this interesting? Is this very similar to what I've seen before, or is it very different from what I've seen before? And then you can use that as an input into where you want to continue testing.
So are you using AI ML here to do that correlation?
Yeah. We actually find it's funny. For many application domains and in many situations, it's overkill. Like you actually find almost all the bugs with much simpler methods once you've got some decent randomness in there and some decent fault injection. But we are currently doing some very cool research with this that we think is gonna drastically improve our results, which I cannot quite talk about yet. But we'll probably be announcing it soon.
Could you give us a hint?
I've said too much.
Sure. I can't wait to see it. What about limitations? I mean, cost sounds like one, but when would this be a completely inapplicable or ill-advised case?
Yeah, great question. I think that costs, people often focus on costs, and I think that this is like very silly. Of course, I would say that, but no, I think it is very. I think it is very silly because what people are currently doing is costing them so much. Like you go and you talk to engineering leaders, engineering managers, and you're like, "How much money do you spend on testing?" And they're like, "Oh, we don't spend any money at all. We don't buy any tools." And then you're like, "Okay, how much time do your engineers spend answering pages, triaging production issues, writing tests, maintaining tests that are broken, like blah blah blah?" And they're like, "Oh my God, they spend all their time doing those things." I'm like, "Okay, great. How many engineers do you have? How much are you paying them?" Like, you're spending a huge amount on the stuff, right? But people don't always think about it that way, but they are. And I think that's one of the challenges is to make people realize that they're already spending millions and millions and millions of dollars on this. In terms of what is a bad fit, I think the main things right now are, number one, if your program is basically just like a straight line, in some sense, if it's very easy to test in a conventional way, because there's not a lot of concurrency, there's not a lot of like network chatter, right? It's just like a small stateless function that does something and you can write some unit tests for it pretty easily. That probably doesn't justify the pain and hassle of trying to test it this way. If you're running on exotic hardware, like we certainly cannot support you today, and if you're using a vast number of third-party external dependencies, that's something that we're going to have a very hard time, for now, dealing with, because we haven't written a mock for every single one of them yet. I would say those are the main categories of limitations.
I want to contrast it with one, I don't want to call it a technique, but one different idea. If, let's say, programmers or libraries or developers could annotate or inject annotations in their code base, which actually explicitly was able to assign error probabilities, how compatible would that be with what you're doing, and how much would that alleviate that initial pain?
I think that's a very interesting idea. So one thing that we actually do encourage our customers to do, if you're thinking about annotating, one thing that I think is a very, very powerful technique is something called bugification. And the idea of bugification is, suppose you have some code which usually does one thing, but very rarely could do something else, right? For example, it could be like writing to a disk, right? Usually it writes all the data to the disk, but as every systems programmer has learned the hard way, sometimes it writes some of the data to the disk and gives you a special return code that says, "Hey, I only wrote some of the data." By the way, networks work the same way, right?
Well, usually flush and fsync are actually not on by default. So,
well, that's true too. Yeah, right. So, right, anytime you have something like this that usually does one thing but very rarely does something else, if it's actually great if you're the one maintaining that code to basically add a little macro around it or add a little thing, annotation, which says, "Hey, if I'm running in test, I'm going to do the rare thing on purpose. Sometimes I'm going to roll a random number. And maybe 10% of the time, I'm just not going to write all the data. Or like 10% of the time, this thing is going to throw an error, even though it doesn't have to, just to test what happens on the other side. Like, is somebody catching that error correctly? Is somebody handling that return value correctly? That can drastically accelerate bug discovery as well.
Okay, cool. Switching back to real world examples, I heard about Ethereum's, the merge in 2022, and you also mentioned Warp Stream. What were some of the most trickiest, kind of scariest bugs that you helped them uncover?
Specifically for Ethereum or for anybody?
Oh, I also wanted to bring up Warp Stream because you mentioned it earlier.
Yeah. For Ethereum, I think the scariest bug we found in Ethereum, I can talk about it now because it's long ago been fixed. We found a very, very scary denial of service bug, which I believe was actually in their protocol. And they had to change their protocol to address it. Their former head of security was the one who's telling us about this. He basically said that it would have qualified for the very highest tier of their bug bounties. It was a bug that would allow you to essentially DDoS the Ethereum blockchain very easily by sending certain maliciously crafted messages to nodes. You could basically cause them to shut down or like start using 100% CPU and not doing anything else or something like that. It was pretty alarming. One of the very first really scary bugs we found was for MongoDB. This was a huge win for us and for them and for our relationship together. We had been collaborating with them, but in like our thing was brand new and it was experimental and they were trying it out. And like, it was sort of like, hey, let's just see how this goes. Not like serious or anything. And then right before they were going to ship a major release, we found a very rare but very severe data corruption bug in their Wired Tiger storage engine, which could basically corrupt completely arbitrary data in any Mongo instance. And it was very rare and it was very hard to make happen. But with the perfect determinism of DST, we could make it happen as much as they wanted and enable them to debug it really, really efficiently. And so that was like a very cool win for them and for us. And that bug has been written up in extensive detail by one of their engineers, both on our blog and also on their Jira. I can provide a link for that if you want.
Yes, please.
Cool. It's a really good one. It's Wired Tiger bug number 9500. I still remember the number.
What was the trigger for this bug? I mean, what was the rare trigger that would have made this bug happen?
Yeah, I'm trying to remember the exact details. This was a few years ago, but basically it involved their storage engine, and their storage engine is like a highly, highly concurrent thing, right? Storage engines have to be highly concurrent because disks are very slow. And so you need a lot of throughput and a lot of latency hiding in order to have a good performance storage engine. But you also don't want to take like a ton of locks everywhere, because if you do that, then like write operations targeting different parts of your database could block each other, and that would be bad for performance too. And so much of the difficulty of writing a storage engine is you're trying to hide all the weird performance characteristics and weird abstractions of a disk and make it just like appear like a very uniform, right? Even when you have operations that could logically depend on each other or not. And I think we found a bug that involved like, there was some lock that should have been taken that wasn't, but it only happened if there was a compaction occurring at the same time that something else happened. And you needed like a particular shape of query. And it was like, I'll send you the write-up. It's like it's a pretty gnarly one. Like I used to be a database guy, and I looked at this bug and I was like, oh my God, I would not know how to fix this. It was pretty bad. I'm trying to think of other good, really scary bugs that we found for people. So we've done a bunch of testing for NATs, it's one of the Linux Foundation projects or CNCF projects. Mm-hmm. They're sort of a distributed sort of software-defined network, and they also have a bunch of like cool storage primitives and consensus primitives and stuff like that. We found a bug in their Raft implementation, which I think they also wrote up for our blog. It's a really cool bug. It requires several things to go wrong. Like a node has to get excluded from the cluster right when something is happening, and then it gets restarted and it comes back and it thinks it's like one of these classic distributed systems bugs. Yeah, I mean, like there's no shortage of crazy bug stories around here. A lot of our customers like have fun writing them up for us. So there's actually a decent number of these on our blog.
Oh, thank you. Can you share some metrics around how you quantify, I guess, I don't want to use the ROI word, but once they see it, before they see it, how do you kind of quantify this?
Yeah, so the customer who's done the most quantification for us was actually Mongo. So they did their own internal study and analysis of their use of us. And they basically found, I think the results actually surprised them a little bit. They surprised us too. They had, in one period of time, 100 really very significant release blocking, could have done something quite bad in the real world, bugs introduced in their development process, right? And I should be really clear here. These are bugs that came nowhere close to getting to customers, right? These were all fixed, and like Mongo is like really good at this stuff, and I think this like the fact that they're studying this and quantifying this really shows you how seriously they take it. But basically, of those 100 bugs, 77 were only found by us, which is pretty cool. And then here's the next part. Of those bugs, they found that the average time to fix them was massively lower if we found the bug. They were like fixed in half as much time, and they were able to be fixed by much more junior engineers.
Is that because your discovery would identify all the scenarios that would need to be triggered in that bug as opposed to guessing what's going on?
Yeah, that's a huge part of it is we have the determinism, right? And so we can just replay that bug, right? Like so much of the hard part of debugging is you never have all the information you need, and you may not be able to get that bug to happen again, right? Like an analogy I really like to use is it's like a police investigation, right? Like when a server crashes, like you have to put up the yellow tape so like nobody's going to step on that crime scene and like ruin the evidence or something. It's like anything that you do in production could potentially make the bug go away. And then you don't. And so really senior engineers get good at guessing. And they get good at like, they know these systems like the back of their hand. And they're like, oh, I've seen that. I saw this one time 3 years ago. I know what this, right? Like, but as soon as you have determinism, it's like you're doing that police investigation, but you have a time machine. And you can just go back in time and watch the accident happen, like watch the murder happen. And now you know who did it. That's so different. It's such a huge change. It actually implies really big changes in how all parts of the SDLC work, right? Like if you think about it, people log way too much. Like people log so much data. Like this is why observability vendors make so much money. Like it's all log storage. But like, why do people log so much data? People log so much data because they know that some issue could happen. And if it's a 1 in a million issue, but it's really important, they may not be able to make it happen again. And so you better hope that you had that log statement in there so that you can like put together the clues and figure it out. But again, if you have a time machine, you don't need to log all that data. You just go back to before the bug and you look at it happen, or you take a core dump at the right time, or you go dynamically enable your logs right before the bug hits, and then you turn them off again afterwards. There's like such a different attitude and a different approach that like becomes possible once you have this capability.
Damn, yeah. It's awesome. What's getting in the way of adoption?
Oh, I think just that it's brand new. Like I said, the very first people that we know of who were doing this started doing it in 2010. And it was all hidden inside this company until 2015. And then word got out, but it was only possible for extremely fanatical, crazy people to do it because the barrier to adoption was so high, right? And still, a lot of people wanted to do it because it was very effective. But like, we came out of stealth and launched this company 1 year ago. So we are really, really brand new, right? So most of the people who we talk to, they just like, I mean, I think we sound like crazy people to them. Like, they're like, we're trying to explain to them there's this like completely different way to have confidence in your software and to get way more confidence in it and to save yourself tons of time. And, I think as with anything, like the computer industry, the tech industry loves to think that we're very, very forward looking, but actually people are creatures of habit. And that's especially true about developer tools, right? And so I think a lot of this is just like, we need a little bit of time to like move the industry in this new direction.
I think it's only now that time traveling debuggers are kind of taking on. So
That's right. And that technology has been around for 10, 20 years. Yeah, 30 years. Yeah. GDB was able to do this like decades ago. Yeah.
Yeah. Looking back at integration, right? Now, obviously, I'm guessing if I was a front-end developer, I may not be as motivated to get on DST. But at the same time, on the other extreme, if I was a kernel developer or a database vendor or a storage developer, this seems extremely, extremely valuable, right? In that spectrum, when would be the sweet spot to kind of start considering this?
Right. So we've actually started seeing really a lot of traction with application developers, but so far it's specifically in the sector of fintech and finance and blockchain stuff. They're definitely doing something more abstract, more high level than a database developer or a kernel or a systems developer. But the thing is that what they're doing is so important, and it's like so important that it not make mistakes, that justifies this like much higher level of scrutiny. So we recently began working with Ramp, which the corporate card, and they have a service that like decides whether to authorize charges on the card. And it's really bad if that like fails to respond to a request, or it authorizes it twice, or that would be not good. And so they really want to test it very, very effectively. And they've been doing that with us. We recently also started working with a large hedge fund. I can't say their name, but it's a big one. And similar kind of situation, right? Like they're moving hundreds of millions of dollars around. They really care that that works correctly. And they really care that every operation is running in the right way.
Looking forward, I think the big buzzword now, AI. With AI writing so much code, and if you've seen the last few days, it's coding for hours and generating, millions in so much on the code, right? How do you see, all that impacting security, bugs, vulnerabilities, and sounds like opportunity?
Yeah, I think so. I think basically, AI can write a lot of code now, and the thing is that people are very tempted to just sort of ship it, right? And to not look too carefully at it, which is not a very good idea if you're in a certain line of work. And so I think it is a huge opportunity for people trying to develop more sophisticated approaches to software verification, right? It really highlights writing code is no longer the bottleneck. Actually, writing code was never the bottleneck, but people thought it was. But like now writing code is really, really, really not the bottleneck, right? The bottleneck is making sure it does the right thing. And that's much harder.
Yeah. I mean, writing is not, reading it is.
Yeah, exactly. Well, that's the other problem with AI, of course, is like it generates a whole bunch of code for you. And then as soon as you want to modify anything about it, you're basically starting from scratch.
How are you seeing adopting to this? Like, do you have to change your approach in how you approach companies? What's your strategy like now?
It hasn't really affected our approach that much, to be totally honest. Like we have a lot of customers who are doing a lot of AI code generation, and they're using us to test the results, right? And probably that segment of our customers will continue to grow over time. Nothing about what we're doing has to change that fundamentally, right? To accommodate this use case. It just means there's more bugs for us to find.
Fair enough. Talking about bugs, you mentioned, was it Mongo who had a high bug bounty? For Ethereum.
That was Ethereum,
right.
Yeah.
Did you guys qualify for that bug bounty, or?
No, we since we were a vendor for them, we didn't qualify for. I wish it would have been a lot of money. No, in the early days of the company, we actually thought about using bug bounties as the primary source of revenue, right? Because like some of them get pretty high, and this thing is actually quite good at finding security bugs too that human beings sometimes miss. And so that was certainly a thing we thought about. In the end, we thought that was a little bit adversarial, and that we would rather be embedded with our customers' engineering team and like making them successful and like improving their lives, making it easier for them to do their job. We thought that in the long term, that would lead to better customer relationships than this like come in from the outside and claim bounties model. But I assume somebody's going to be using either DST or AI or something else to claim bug bounties very soon.
Fair enough. No, it's a exciting kind of future out there. As we wrap up on closing thoughts, what advice would you give to our listeners about improving their own testing practices or evolving their platforms to get ready for DST?
Right. It's really the thing I said towards the start of this is I think the single most important piece of advice. Anytime you see a bug in production, any single time, it is two bugs. It is two bugs. It is a bug in your code, but it's also a bug in your tests. And you should demand more from your tests. You should cultivate the attitude that it is unacceptable for things to go wrong in production. And that if a thing does go wrong in production, you should be asking yourself, what could we have done differently that would mean that we found this ahead of time?
Awesome. For our listeners who want to learn more, how can they do so and where?
Yeah. There's a lot of people who've written good stuff about this. We have some material on our website, antithesis.com. The other people who have talked the loudest and the most about DST, the FoundationDB team has written a bunch of stuff about this. They're now at Apple and a lot of them are at Snowflake. but they've written a ton of good stuff. The FoundationDB paper that came out a few years ago and was in Sigmod is very good. I can send you a link to that. It's got a whole section on how we did DST. The people at Tiger Beetle have written some really good stuff about this. They've done a very good job at it. So I think those are some pretty good resources. And then I gave a talk at Strange Loop back in 2015 about the FoundationDB DST approach. So that was almost 10 years ago now, but it still has some good stuff.
Nice. Thank you. Before we wrap up, is there anything that we haven't covered that you'd like to share for our listeners?
Nope. I think this was a ton of fun. Thank you so much.
Thank you. Will, thanks for being on the show. Looking forward to seeing you live.
Cool.
Cheers.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.